Hello guys, so we're going to be covering section 5.3, which is the fundamental theorem of calculus. So before we start, we need to review just a quick touch on antiderivatives. We gotta I want you guys to remember kind of the notation, the definitions that we use, and so on. So just a quick reminder of what an antiderivative is. A function f is called an antiderivative of little f on an interval I if f prime of x is equal to f of I, well, capital F prime of x is equal to f of x for all x and I. So, given the antiderivative, we want to find, the function we started at. So, this is kind of the case. If we look at 1/3 x cubed, that when you take a derivative of that, we get, x squared. Bring down the exponent, subtract by 1 from it. So, if we want to think about f of x is equal to x squared, we can find the antiderivative by thinking about the the inverse of the power rule, kind of like that. We have some ideas. Basically, it's we have a function f of x. The antiderivative is the function that when we differentiate it, we get back our f of x. So if we what I drew again right here, was that x squared. If we take a that's going to be imagine this operation is derivatives. You take a function, you map it to its derivative. So typically what we've done so far is going from here to there, using the quotient rule, the chain rule, product rule, and so on. But now with antiderivatives, we're going to go from here to there. That's the point of an antiderivative. So just kind of keep that in mind when we talk about this section, because this section is the fundamental theorem of calculus, which relates to antiderivatives. It builds on statements. So now that you kind of have this kind of remembering what antiderivatives are, let's talk about them real quick. So for section 5.3, we're going to talk about the fundamental theorem of calculus. So far what we've done is just more about integrals. We've done definite integrals and how we can solve them using limits. So remember that area under function f from a to b is the integral from a to b of f of t dt. And the reason why I brought up the antiderivative is because in this section, we'll actually, relate the antiderivative to the integral. So far, again, all we have is some area, under some curve f of t going from a to b. But, that might not be useful at all, so far that doesn't give you any obvious intuition to antiderivatives, because at this point, antiderivatives are their own thing. Integrals, their own thing. But the fundamental theorem of calculus takes these two objects that we don't really know about and puts them together. So let's kind of give a basis for that. So let's just say we're looking at the integral 0 to x of t dt. So remember that, t dt, the dt, this part here, kind of indicates what variable you're integrating. And that t is our integrand. Remember that's a function, we want to find the area under the curve. And x is going to be where we're stopping at. So x is going to be a real number, and x is going to be greater than or equal to 0. Otherwise, we'd have to do the negative version, but it doesn't really matter. And, the fact that x is a real number, x is the upper limit, that we're finding the area between 0 and x. That's not so important, but it's important to know is just it's just basically b. B is some number, it's just arbitrary constant, we're just integrating up to there. And that's what we're doing with x so far. X is typically used as a variable, but in this case, t is our variable, x is just someplace, x is our stopping point. So if you look at this integral, under the curve, under the function y is equal to t, because that's our integrand, or, f of t is equal to t, then we can look at the graph from 0 to x. So the fact that y is equal to t tells us that our y coordinate is obviously going to be y, but our x coordinate, this axis right here, really is going to be t. So we're going to integrate from 0 to x. And, considering this is just y is equal to t, and that's just a line, it's going to be a line from going to 0 all the way up to the point xx. And again, that might be a little weird, but the coordinate is actually going to be, the coordinate representations here are ty. So if we look at this, that's a straight line connecting, the point 0, 0 to xx. Then if we look at this is also going to be a straight line. That's also going to be on the axis, and this is going to be the same as well. So this area, this region is just a triangle. And this length right here is going to be x, and because it's just y is equal to t, just like the identity function or just a very simple function, like this length right here is going to be x, this height is going to be x. That's this triangle with base x and height x. So because, like we touched on this briefly on the last section, but we know that, if you just integrate it, like you can use rectangles, otherwise, but in some cases where the region is very nice, you can actually just, actually use geometry, which is what we can do here. So the integral from 0 to x of t dt is equal to 1/2 base times height, so 1/2 x times x, which is 1/2 x squared. And let's call that g of x. So we note that if we know I originally said, we're treating x as like a constant, just x as a constant, like b, we're not going to do anything with it. And the reason for that is because whenever we do Riemann integrals, we have to specify the interval first, it's fixed. And then what we do next is, we build we split up that region from 0 to x into n subintervals. We take the limit of like rectangles, but all that stuff depends on the interval. So if we had to keep x fixed to kind of evaluate the integral. But what happens if we try to, now we treat x as what we think it normally is, like a variable. So what if we just wanted to find the region to 0 to x where x is just any arbitrary number? And the fact is that this still works out. This right here is completely independent. We don't have to do any Riemann sums. It doesn't matter what x is, it still works. So in that case, we get that the region for 0 to x of t dt, we can get that, if we were doing the integral from 0 to 1, say 0 to 1, that would just be g of 1. If it was instead of x, it was or 1, it could be 10,000, then it would be g of 1,000. So what g represents is just the area under the curve going from 0 to the argument of, g, so g of x. Or of x, my bad. But the point is this is now a function. We have a function that gives you the area under the curve going from 0 to x of f of t dt. But we should note that, we look at g of x, which is 1/2 x squared. We take a derivative of that, we get x. So g is going to be an antiderivative of the function, y is equal to x, or, f of t, well, f of x is equal to x, which is our integrand. Originally we had t, but really, we have f of t is equal to t, but really, that could be x, it doesn't really matter. But the point is that this function right here, the integrand, matches up with the derivative of, that function. We had a function that gave us the area, we took derivative of it, we get back our integrand. Now that's pretty weird, that's our, we got the fact that, we created this function, g of x is equal to the integral from 0 to x of t dt, and we got that g prime of x is equal to, t. Well, in this case, x. So that's weird, why does that happen? We don't have any weird linkages here. In this case, it works for all those triangles because they're all just we can define the areas without having to do rectangles. But, how do we know this is true for higher things? How do we know if it's more curvy things, like x squared or cosine of x or anything like that? But it turns out that we do have a nice theorem for that. We have a nice theorem relating the integral to the antiderivative. So this is going to be the fundamental theorem of calculus part 1, or FTC is what we refer to that. So I might say it FTC just because it's a mouthful to say the fundamental theorem of calculus. So F is going to be continuous on AB, so it has to be continuous. Continuity is really nice and required here. We're going to define G, so G is going to be a function. Going to be the g of x is going to equal to the integral from a to x of f of t dt when x is between a and b. So we're going to find the area under the curve of f of t going from a to x. So, and continuity is really important here, which we'll kind of go over later. But the fact is that continuity is required. If we don't have continuity, then things might change. We might not have all the strong properties we have right here. So the theorem says if we have g of x defined this way, if g of x is equal to the area from a to x of f of t dt, then we get that g is continuous on AB, the closed interval AB, differentiable on the open interval AB, and we get that g prime of x is equal to f of x. Now that in itself is where this theorem is. This is the important part of the theorem, is that we just took what we just had and generalized it. G prime of x is going to become an antiderivative of f. So what this means is that g of x is an antiderivative of, f of x. And, that's basically just what we did. Again, it doesn't really matter if it's t or, the variable's t inside the integral. T is just referred to as a dummy variable. When we do integrals, we will say like f of x dx. But if we're integrating to x, then we need to use another variable, so we just usually use t. So this is like where the meat of like this theorem comes in place. Well, it's part 1, part 2 is kind of built on this. But this is awesome. We get to the fact that g of x, this like weird function right here, is an antiderivative of its integrand. And that is like awesome. Honestly, that's really weird, and that's not like, a thing that's like, we built into it, like, we had Riemann integration, which is basically just like, areas under the curves approximating with rectangles, taking like arbitrarily large like number of rectangles. And we also just like, we found areas of tangents, and we just kind of linked them together. Well, not areas of tangents, but, slopes of tangent lines. So let's do an example real quick of this. So let's just say h of x is going to equal to the integral from 5 to x of the cube root of 1 plus t cubed dt. So f of t is going to equal to the cube root of 1 plus, t cubed, because that's, the integrand. That is continuous. It's just a polynomial. It's not defined. It's nice. Well, it's a polynomial inside a radical function, but the radical function is cube root, so it's defined everywhere. It's all nice. So by part 1 of the fundamental theorem of calculus is that we have h prime of x is equal to the cube root of 1 plus x cubed. So if our h is defined this way, then by FTC, we get that. So, so far that's nice, but, we could actually generalize that a bit more. We could do, instead of integrating to just x, we could do something else. We could integrate to, another function like g of x, for example. So, in this case, it still works the same. But let's do, more concrete example. Let's do d of dx of the integral from 1 of x to the 4th of secant of t dt. So, remember that, the function g of x is, gives you an area. It gives you the area under the curve for some function from like a to b. Well, a to x. And if we add like, x to the 4th, what that does is like when we change that x value a bit, now that change in x is going to be a lot bigger corresponding to that x to the 4th. So the fact that we have x to the 4th here means we're going to have to use a chain rule. There's an x here. Typically when you have like, function, like if you want to think about it as like, g of x is equal to integral from like 1 to x of secant of t dt, if you want to think of it like that, where then you would have to do g of x to the 4th, and you would get, 1 to x to the 4th. So this is kind of where you can see the composition. The fundamental theorem of calculus only talks about the case where you're integrating from 1 to just x. Or not 1 to x, but some number to x. And it could be the lower limit, but, all you'd have to do is just do the negative of that. But, that doesn't matter so much. So the fact is that, there's an x to the 4th there. And because of that, we have to use the chain rule. So we have this chain rule along with part 1 of the FTC, since x to the 4th is our limit. So we just do a u substitution. U is equal to x to the 4th. Let's kind of do like a chain rule kind of thing. That way you can understand what's going on and just write it in a different way, in a way that makes more sense. So d of dx is gonna, that thing we're gonna differentiate, d of dx of the integral of 1 to x to the fourth of secant of t dt, and that's a lot of words. That's gonna be the same thing as d of dx of, now we're gonna place u inside. Remember that u is equal to x to the fourth. And remember that, when we had like dy dx, and whenever he had like u is equal to like f of x or whatever, u is dependent on x and y is equal to something with u in it. Then what we had was, du dx, well, no, it was dy dx. Okay, my bad. dy du times du dx. So in this case, this is going to be like our y right here. So that's going to be d of du now. Because that's basically what this piece represents, is dy du, but really we need to have d du because we haven't taken the derivative yet. So d of du of the integral from 1 to u of secant of t dt. And we still have to kind of multiply that piece right there, so du dx. And again, that's by the chain rule. Because when we do the substitution, for this u, we have to substitute with the derivatives as well, but because we're substituting in with the derivative as well, we have to multiply by the chain rule part. So by FTC, this tells us that d of du of the integral of 1 to u of secant t dt, that's just, secant of u, the integrand evaluated at u. We still have times du dx, but, again, u is equal to x to the fourth, so du dx is just going to equal to 4x cubed. So du dx is equal to 4x cubed, u is equal to x to the fourth, so we get secant of x to the fourth times 4x cubed. And this problem is a little weird, but you just have to understand that, like, I'm going to try to do it in a different way. So let, g of x equal to the integral from 1 to x of secant of t dt. Then if we plug in, g of x to the fourth, we just get that. That's going to be g of equal x to the fourth. So now let's just say we wanted to find the derivative g of x to the fourth. Prime, this is basically the same thing right here, but with function notation. That's going to be g prime of x to the fourth times, x to the fourth prime. And that's like the chain rule. So remember that, g prime, in this case, we would have to evaluate that using the FTC to find out what g prime is. And in our case, g prime was equal to secant of of u times really it would just be secant of t, but we plug in x to the fourth, so secant of x to the fourth, and then it would be times the root of x to the fourth, which is 4x cubed. So it might be a little weird, but just kind of keep in mind that this is what's going on. All right, so that's confusing, but it just takes a bit of time to work on it. And especially to kind of see what is going on. Just the idea is, g of x is just going to be a function. You do the chain rule, so you'd have to take a derivative of the inside, so take a derivative of just the integral, and then ignoring the upper the upper limit. And then whenever you do that, you would actually plug in the upper limit and then just multiply the derivative of it. All right, so ignoring that weirdness, but let's go to the fundamental theorem of calculus part 2. And the reason why I just say it's weird is just because, it is weird. But the fundamental theorem of calculus part 2. So let's just say f is continuous on some closed interval AB. And note that continuity on a closed interval is really, really nice. Continuity is basically kind of what we need to make these things have meaning. And the closed interval AB is because, if we look at the extreme value theorem, that's going to be that's the only thing you need there is continuity on some closed interval. Because, if we have a set AB like this, then we could have a vertical asymptote at A, we could have vertical asymptote at B, we could have a lot of weird things happening. And the closed interval basically requires us to have all these nice properties. So I'm kind of rehashing that a lot because it's important. A lot of our theory is built on these closed intervals. So if f is continuous on the closed interval AB, then we have the integral of a to b of f of x dx. is going to equal to capital F of B minus capital F of A. And the notation that we kind of use this, considering these f's or capitals f's are functions. So capital of f of x evaluated at AB. And you might also see this as like AB, and depending on like, some of the notation, you might write it like this. That way it's a bit more clear. But the point is those brackets with things written like that kind of indicate we're doing the difference between the top and bottom. So what does this mean again? Is that f where, but because we're going to define, sorry guys. All right. So the integral from a to b of f of x dx is going to equal to capital F of b minus capital F of a. And what is the capital F? Capital F is going to be any antiderivative of f. So we don't really care what the derivative is. I mean, we don't really care what antiderivative, it just means an antiderivative. It doesn't matter which one, we just got to choose one. And that's very important, especially to the fundamental theorem of calculus, because if we want to evaluate an integral, the only thing we need to know is just the antiderivative. We need an antiderivative. And this is where those come in. So we want to do an example of this real quick, and then we'll kind of get more into the details of it as we do it. So let's try to evaluate the integral from 1 to 5 of 1 over x dx. So an antiderivative of f of x, is equal to 1 over x. We've already kind of done this before, is going to be capital F of x is going to equal to ln of the absolute value of x. And again, it's absolute value because this is going to be defined from negative infinity to 0, union, 0 to infinity. The fact it's defined on, weird side doesn't matter, but we only care about it from 1 to 5. So whenever that capital F of x is equal to the ln of the absolute value of x, then that's going to be an antiderivative. So the fundamental theorem of calculus part 2, so this statement right here, is going to tell us is that the integral from 1 to 5 of 1 over x dx is going to equal to ln of the absolute value of x evaluated at going from like 1 to 5, or like, I don't really know how to say that, but that's just like the notation. It's going to be the ln of the upper limit minus the ln of the bottom limit. So we plug in the top limit, so ln of 5. We plug in the bottom limit, we get ln of 1, you take their difference. We get ln of 5 minus ln of 1. Ln of 1, that's just equal to 0. So we just get ln of 5. And no, we don't have to worry about the plus c when evaluating definite integrals. So technically, the most general antiderivative of, f of x will just be f of x equal to the ln of the absolute value of x plus c. But we'll explain why that doesn't matter in a second. But again, all we did for this problem was, we found an antiderivative, we figured out what our integrand was, so 1 over x. We found an antiderivative of f of x, and we said that was equal to the ln of the absolute value of x. And we just used that information to find this difference right here. So this was like f of 5 minus f of 1, because this is the part that's important. And then that's going to equal to ln of 5. And, that whole statement in itself is very nice. This basically gives us a way to calculate definite integrals. We could, we could use Riemann sums, we could use rectangles, we could take limits. But now, instead of doing all that, we can just, use antiderivatives. If a function 1 over x has a very nicely defined antiderivative, then we can use that antiderivative. And when it has an antiderivative, then we can use that antiderivative. We should note that this says any antiderivative. And the first fundamental theorem of calculus says is that this function g of x, defined this way, is an antiderivative of f of x. So this links us between, areas and, integrals and derivatives, because this basically says, okay, well, now we can talk about definite integrals in terms of antiderivatives, which is super nice. And again, the most general antiderivative of f of x is equal to 1 over x. That's just going to be equal to capital F of x is equal to ln of the absolute value of x plus c. Basically, you take the general one, you add plus c to it, and you get the most general one. And again, the absolute value, like not the absolute value, but the fundamental theorem of calculus part 2 requires that we use, f of b minus f of a, where f is any antiderivative. And the reason why it says any is because the most specific one would be plus c. So if we use plus c, if we make a general, we get ln of 5 plus c minus ln of 1 plus c, because again, this is going to be f of 5 minus f of 1. So we plug in 5, we get ln of 5 plus c, plug in 1, we get ln of 1 plus c, take their difference, and we get the ln of 1 is just 0, so we get c minus c, so that's just going to be 0, so we just get ln of 5. So the c's cancel, so we don't really care about them. But if there are no limits, if we didn't write the limits for whatever reason, then we would have to include the plus c. But we will talk about that in the next section. But, let's use that. Let's use the integral, again. Well, let's use that, fundamental theorem of calculus part 2 again to kind of evaluate the integral. So let's evaluate the integral from 1 to 2 of 4 plus u squared divided by u cubed du. And again, the u's don't matter. We're just trying to integrate with respect to some function. So the integral from 1 to 2 of, all that jazz of the integrand, we're going to break up the u. So, break up the fraction over its denominator, get 4 over u cubed plus u squared divided by u cubed. So, all we did was just, simplify the inside. We rewrote it to be a bit nicer, so 4u to the negative 3 plus 1 over u, because that's just u squared divided by u cubed. And now we have to find an antiderivative. So again, our integrand is going to equal to f of u is equal to 4u to the negative 3 plus 1 over u. We got an antiderivative, it's just going to be this right here. Because, u to the negative 3, we want to find an antiderivative, but it's basically the opposite of the power rule. So the power rule, again, is, when you take a derivative, you bring down the exponent, subtract by 1. So the antiderivative would be plus 1 to the exponent, then divide by that exponent. So it'd be 4u to the negative 2 divided by negative 2. Because again, that'd be, plus 1 divided by negative 3 plus 1. And then we have already said that an antiderivative of 1 over u would just be ln of the absolute value of u. So we get for that an antiderivative is going to be capital F of u is equal to negative 2 divided by u squared plus ln of the absolute value of u. And that's going to be by part 2 of FTC. So that's what we have, is that the integral from 1 over 2 plus 1 over 2, the integral from 1 to 2 of 4 plus u squared divided by u cubed du. That's going to be equal to, the antiderivative, where it's going to be evaluated at 2 and 1, and then you're going to do their difference. And again, that's not squared. This is what this means is f of 2 minus f of 1. So that's all we did. Plugged in f of 2, plugged in f of 1. We get negative 2 divided by 2 squared plus ln of 2 minus, negative 2 divided by 1 squared plus the ln of the absolute value of 1. And all we did was simplify, ln of 1 is 0. We just get all this. We just do some algebra now. And we get ln of 2 plus 3 halves. So in this case, again, all we did was we found some antiderivatives of the integrand. And then once we had the integrand, we just did, once we had an antiderivative, we just did, f of 2 minus f of 1. And then, whatever value we got for that is going to be the value of the indefinite integral. Well, it's going to be the value of the definite integral, my bad. It's not the indefinite one. All right, so, we can have, okay. So we got to be careful with, doing the fundamental theorem calculus, because if we're not careful, we can have some issues. Having an antiderivative is nice, but only if we use it properly. So let's look at this quick example before I kind of explain. So this is going to be the integral from negative 2 to 1 of x to the negative 4 dx. We can find an antiderivative. Plus 1 to the exponent, divide by the negative, divide by the new exponent to get x to the negative 3, divide by negative 3. So negative x to the negative 3 divided by negative 3, that is indeed a antiderivative of x to the negative 4. We plugged in, 1 to that minus 2. Well, we did the difference. And we did the difference, and we got negative 3 divided by 8. So that's the correct answer, sort of. That's the correct, this right here is the correct. But there is an issue. So let's just take a notice at it real quick. Is that we're integrating the function f of x is equal to 1 over x to the 4th, which is going to be greater than or equal to 0, so it's non-negative. So the area under the curve must also be non-negative. So if you integrate something positive or something that's 0, then you should either get positive or 0. But it can't be negative. But the answer that we got was a negative. We integrated a positive function, and we got a negative answer. So this has to be wrong. This is not correct. And why is it wrong? And the reason why is because FTC only applies to functions that are continuous. So continuous on the closed interval AB. But f of x, which is equal to 1 over x to the 4th, the function that we were just talking about, is not continuous on negative 2, 1. So the fundamental theorem of calculus cannot be applied here. And we can see that because it's 1 over x to the 4th, so it's not defined when x, as x is equal to 0. So x can equal 0 here. So really we're integrating over negative 2 to, 0 union, 0 to 1. And because of this gap right here, because of this hole, we can't use the fundamental theorem of calculus. It only works for closed intervals, closed intervals like this, including the endpoints, and when you have continuity. If you don't have continuity, then you can't do this. And whenever you do Calc 2, you'll go over into you'll actually go into examples of examples. We'll go over methods on to find these intervals. How would you evaluate them then? If you want to make some sense of them, can you even integrate over vertical asymptotes? And the answer is yes, but it's got to be specific in some cases. So this section right here, section 5.3, what we basically did was we found some ways to find derivatives. Well, we find integrals. We want to evaluate integrals, and the way we can talk about them is in terms of antiderivatives. And what we get is that the antiderivative, an antiderivative of f of t, the integrand can be evaluated using an antiderivative of it. And that is incredibly powerful. It's super nice, amazing, I don't know, man. To me, it's really cool. And part 1 basically says, if we try to find the area from a to x of f of t dt, this function right there, then what that is that is also an antiderivative. And that's pretty awesome, actually. That allows us to do a lot of things. It allows us to differentiate, a lot of functions, try to find out good representations for them, and so on. But really, the most important part comes from part 2. Because this basically tells us that instead of doing, Riemann sums, instead of doing limits, instead of doing rectangles, instead of doing infinite sums and stuff like that, we can just now do antiderivatives. All right, but that's pretty much it for this section, though. It's kind of weird at first, but it's really powerful. And if you want to know what to focus on, just focus on part 2. Part 2 is awesome. So explaining, if you could do this example, and this example right here, pretty nice, then that'd be awesome. All right, thank you guys for watching. Hope you guys like, comment, and subscribe, I guess. Peace out.